Hey everyone, welcome to our talk, Bugs on the Windshield, Fuzzing the Windows Kernel. We're really excited to be here today. It's an amazing venue with lots of great people, and we hope you enjoy this presentation as much as we had doing the research. So a little bit about us. My name is Yoav Alon. I'm the CTO at Orca Security, and I've been a security researcher for the past 10 years. Also, recently I was added to MSRC, Most Valuable Security Researcher for 2019.
My name is Netanel Ben Simon. I'm a security researcher at Checkpoint Research, and I'm also in the same list as Yoav.
So our motivation for this research is that we love fuzzing. We really do. But also, we had a pretty successful fuzzing campaign against binary format parsers in user space. We found multiple vulnerabilities in formats such as JPEG, GIF, EMF, WMF, and so on, mostly targeting Adobe Reader and Microsoft Edge. If you're interested to read more about this research, you should check out Checkpoint Research blog. We have everything about the methodology and anything else. So at this point, we were wrapping up the previous research, and we felt that we wanted a bigger challenge. And fuzzing Windows kernels seemed hard enough. And as an added bonus, we can take one of our existing user space vulnerabilities, chain them together with a newly found kernel vulnerabilities, and create a full chain. So a few obligatory slides, since this is a presentation about fuzzing. Fuzzing is a method for automating. I'm just kidding. This is OffensiveCon. We're not going to do introduction to fuzzing. We don't have time for that. So anyway, we were at the beginning of the research, and we said to ourselves, we have a lot of experience with AFL. Can we use AFL to attack the Windows kernel? And the answer is pretty surprisingly, not unsurprisingly, yes. There's KFL, which is AFL with a K. And K stands for kernel. So KFL is a research fuzzer from the Bochum University that leverages AFL-style fuzzing for attacking Windows OS kernels. It supports Windows, Linux, and Mac OS, and it was used to find real bugs in real software, which is what we want. KFL has a pretty interesting architecture. We're going to review it quickly because it's important for the rest of the presentation. The main fuzzer runs on the host, and when it starts, it will spawn multiple virtual machines that are running the target OS. In the guest OS, there will be a preloaded agent that will cooperate with the fuzzer to drive the fuzzing process forward. The fuzzing looks something like this. The agent will request an input from the fuzzer. The input will be transferred through shared memory. Then the agent will request from the hypervisor to record coverage. We're going to talk about exactly how in a moment. Next, the agent will pass whatever buffer it got to whatever it wants to attack, in this case, test sys. And finally, it will stop coverage. It will notify the hypervisor to stop coverage, and the coverage will be transferred to the fuzzer. So how is KFL able to generate coverage traces? Well, it uses Intel processor trace, which is also known as Intel PT, which is a low overhead hardware execution tracing feature that supports tracing coverage for each hardware thread. The trace information is written in compressed form to physical memory, and KFL uses a fast decoder to generate full traces from the compressed form. Finally, crash detection. It's pretty cool. When the agent is first loaded, it will send the addresses of bugcheck and bugcheckx to the kernel, to the hypervisor, and the hypervisor will patch those addresses with a special shellcode that will issue a hypercall. When the system will crash, the patched kernel will call bugcheck and bugcheckx, which will issue the hypercall, which will notify the fuzzer about the crash. So let's do a quick recap of how a harness looks like. We start with a hypercall that tells the hypervisor to monitor this process. Then we assign a buffer to where to write the inputs. And then in an infinite loop, we will first ask for a new payload. We will try to start tracing coverage, pass the buffer to whatever we want to attack, and finally tell the hypervisor to stop tracing coverage. Here's a screenshot of KFL running. If you blink fast enough, it kind of looks like KFL. So what can we attack with KFL? Or what can we attack with AFL? So from our experience, good targets for KFL and AFL are fast targets, ones that are able to execute hundreds of iterations per second, and parsers, specifically for binary formats. So what binary format parsers live inside the Windows kernel? So there are quite a few. There are file system and file system-like formats like NTFS, FAT, CLFS, VHD, registry. There are device drivers that parse binary format. There are the cryptographic drivers that parse binary formats. And there are quite a few others. But at this point, we took a step back and we said to ourselves, let's look at a typical kernel bug. In this case, CVE 2018-0744. If you look at this, you don't have to read it, just look at the structure. There are multiple system calls here that take as input highly structured data, like structs, magic numbers, function pointers, strings, and flags. And they have dependencies between them, meaning that the call for an output of one function is the input for the next function. And this is pretty common in kernel bugs, that there's a sequence of calls that put the system in a state where vulnerability is triggered. But notice that there are no binary parsers here. And these are the kind of bugs we want to find in this research. So if we take a step back, unfortunately, what KFL provides us is a binary blob. And what we want is a sequence of syscalls that semantically makes sense, preferably as a C file. So, and if we look back at the attack surface again, and that we had with binary parsers, and we go back and look what a syscall fuzzer can give us, we can see that now the map is much better. We can attack much more of the kernel, and that's good for us as attackers. So we decided to dump KFL and move to a syscall fuzzer, and we did what every good researcher does. We used Google to search for a syscall fuzzer. And that's how we found Syscaller. Netanel will now come and tell you all about Syscaller.
Thanks. Okay. Syscaller is coverage-guided, structure-aware kernel fuzzer. Try saying this 5 times in a row. It's also known as Smart Syscall Fuzzer. It supports multiple operating systems such as Linux, FreeBSD, Fuchsia, Adroid, and more. It supports running on multiple machine types such as QEMU guest, Google Cloud Engine instances, mobile phones, and others. It also supports running on multiple architectures like x86-64, 64-bit ARMs, and others. Syscaller is also known in some circles as the hardest working researcher in the Linux kernel community. To date, it has found around 3,700 bugs in the Linux kernel. One example is CVE 2019-2215, which Mehdi presented earlier, a use-after-frame binder which was found being exploited in the wild. As you can see in the screenshot from Sysbot, Syscaller's online dashboard, it was found 2 years prior by Syscaller. Modern fuzzers have few common characteristics. They have a smart test case generator mutator. They use a feedback mechanism, usually a code coverage, to drive the fuzzing process. And they employ sophisticated bug oracles for detecting crashes. Let's see how Syscaller answers these criteria, starting with test case generator and mutator. Syscaller generates programs, which are a sequence of syscalls. Let's look at an example of a program generated by Syscaller. This program opens a file called file0 and assigns its result to R0. This weird pointer assignment syntax are instructions to write the string file0 to memory and pass this pointer to the open syscall. This syntax is not only used for strings, but also for describing memory layouts of structs, buffers, unions, and others. Next, the program reads 57 bytes from the file to memory. And finally, it closes the file. But how is Syscaller able to generate programs? Well, it uses Syscall Descriptions. Syscall Descriptions are how you as a researcher define to Syscaller how to generate syscalls. It's basically the recipes used by Syscaller to bake programs. Let's look at a simple description. For example, the syscall exit, which has only one parameter, the error code, which is an int. Notice that Syscaller uses a Go-like syntax, where the type comes after the argument name. A more complicated example is the close syscall, which receives a file descriptor, which is technically an int, However, we know that file descriptors are a handle to kernel resource, meaning that random numbers will just be rejected by the kernel. That's why Syscaller has the concept of a resource, which is a type that it cannot generate by itself, but it has to use other syscalls to obtain it. An example of syscall that returns a file descriptor is the open syscall. Syscaller also supports flags, structs, unions, and others. In the case of open, it knows that open mode is a flag, which means it can use one or more flags together. Last example is the read syscall. The syscall receives buffer as an input, which it will write up to length bytes to it. Notice that length and buffer have a semantic relationship, meaning that the length should not be bigger than the buffer, otherwise it will probably fail. Syscall descriptions are written to text files. syz-sysgen, which is Syscaller tool, will take the syscall descriptions and automatically generate Go code that will be compiled into syz-fuzzer. syz-fuzzer will then use the syscall description to generate programs by randomly selecting syscalls and making sure to satisfy their dependencies. Syscaller is also able to mutate existing programs with a few mutation strategies. Insert call, well, insert a call, making sure to have all required dependencies to successfully call the syscall. Mutate arg will mutate an argument according to its type. Splice will take two random programs and join them. And squash any will perform AFL time mutations on complex pointers, such as structs, buffers, unions, and others. So clearly, Syscaller has a sophisticated test case generator and mutator. Moving on to feedback mechanism. Now that we know how Syscaller generates programs, let's look at the bigger picture. The main binary for Syscaller is syz-manager. When it starts, syz-manager will do the following. It will load the corpus of programs. Then it will start the target machines. It will copy the fuzzer and the executor binaries to the machine using SSH and execute a fuzzer. At this point, syz-fuzzer will establish connection with syz-manager and start communicating by RPC. Syz-fuzzer will then fetch the corpus and start generating programs. For each program, it will send it back to the manager for safekeeping in case of a crash. Then syz-fuzzer will send it to the executor, which will run the syscalls and collect coverage from the kernel. We will talk in a moment about Linux kernel coverage, how it's done using kcov. Then syz-executor will send back the coverage to the fuzzer, which will notify the manager in case of a new coverage. Linux kernel coverage is done using kcov, which is a compile time tracing feature. It uses the coverage sanitizer, fsanitize, trace pcguard. For example, we can see that kernel func has few possible code paths. We would like to know for each path if it was visited. In order to do this, the compiler will add an instrumentation to each basic block, which will call a callback function that saves the instruction pointer to a per-thread buffer. Coverage collection in user space is like really easy. You generally assume there is only one thread and everything is deterministic and fun. In kernel space, however, coverage collection quickly hits a few roadblocks. Interrupts will appear and randomly appearing randomly in the trace. There are background threads that are used to process some syscalls. There is a general non-determinism from interaction with hardware, and flags caused by scheduler or allocator behavior. To handle coverage flags, Syscaller employs a mitigation technique, a coverage mitigation technique. First, it defines two types of coverage. The minimum coverage, which is the coverage trace that is contained in the minimum coverage, and the maximum coverage, which is all the coverage that we ever encountered. If a program coverage trace is contained within the minimum coverage, then we will discard it. But if Syscaller detects a new coverage, which is not contained in the minimum coverage, it will run the program 3 times, and will only use the coverage that was consistent between all the 3 runs. So it will add the deterministic coverage to the minimum coverage, and the non-deterministic coverage to the maximum coverage. Coverage feedback mechanism, check. Finally, bug oracle. In case of a crash, Linux kernel will panic and print crash information into the console. sys-manager will detect the panic message and report on a crash. Syscaller is usually used with ksun and optionally with ktsun, kmsun, and other suns, which greatly improves Syscaller's ability to find buggy conditions. Bug oracle, check. Syscaller aims to be unsupervised, meaning it will try to automate the entire fuzzing process. In an ideal world, fuzzers are just plug and play. But like Charlie Miller used to say, working with fuzzers is like babysitting an army of monkeys. In the case of crashes, sys-manager will spawn multiple reproducer machines. In the process of reproduction, Syscaller will dissect the crashing program from its logs and will minimize them. When the process is finished, most of the time it will reproduce either a sys program, like we've seen earlier, or a C code, which reproduces the crash. So to recap, Syscaller is awesome. But Syscaller is for Linux. So actually, before this presentation, we talked with Dmitry Vyukov, which is the father of Syscaller, and he corrected us that Syscaller is not only for Linux, but supports other operating systems as well. So when we mean Syscaller is for Linux, when we say Syscaller is for Linux, we actually mean Syscaller is also for Linux. But we want to fuzz Windows. So let's run Linux on Windows. What is WSL? WSL is a compatibility layer for running Linux binaries natively on Windows. It translates between the Linux syscalls to Windows system calls. Allows to interrupt Linux and Windows binaries. For example, we can run task list from bash and count the number of lines. It requires less resources than running a full virtual machine. And finally, it was designed to bring developers back to Windows, to run bash and call Linux command for developers. So let's see how does it work. Starting from Windows 10, there is a new type of lightweight process called Pico process. When a Pico process issues a syscall, it will pass from the anti-kernel to a dedicated driver called Pico provider. In the case of WSL, the Pico processes are Linux binaries, and the Pico provider LXS and LXCore will translate the Linux syscalls to anti-system calls. So at this point, we decided to start with WSL because fuzzing WSL is very similar to fuzzing the Linux kernel. So we can reuse most of the existing grammar and the binaries. It is relatively new, and has a big attack surface, 2 drivers which are around 1 megabyte in code, with little CVEs. And finally, we wanted to find bugs for full chain, but we also wanted to get some experience fuzzing with Syscaller on Windows. So it looked like a good first step. Looking at Syscaller architecture, we need a few things to change to fuzz WSL. We need an SSH server, which is easy. We have a Linux distro for that. We need to find a way to collect coverage. And finally, we need a mechanism for crash detection and crash de-duplication. How to get tracing coverage? Windows is closed-source compiled binary, meaning that we can't use a compile time tracing feature like kcov. So we thought of a few alternatives. The first option was using an emulator like Box or QEMU and adding coverage instrumentation. The second option was using static binary instrumentation for coverage, like PAFL. Another option was using a hypervisor with sampling coverage, like ApplePie. But at the end, we settled on using Intel PT for coverage, like KFL. What we did was to add patches to KVM to support coverage with Intel PT. So we used large parts of KFL's KVM patches for that. In addition, we exposed the executor a K-code-like interface. So now when the executor tries to start, stop, or collect coverage, it will communicate with the KVM instead of the kernel. We also support for exporting coverage in Dynamo coverage format, also known as the RCO format. And we used the IDA and the awesome Lighthouse plugin to visualize the coverage. Here's an example of how Lighthouse visualizes the coverage by adding colors to the executed basic blocks. As for Bug Oracle, we use the same technique as in KFL. In case you already forgotten, we patch bugcheck and bugcheckx with a shellcode that issues a hypercall on a crash. We also added a regex to identify crashes from QEMU output. And finally, we enabled driver verifier with special pools for LXCore and LXSS to catch pool corruptions. A common issue with fuzzers is that they encounter the same bug many times. When the fuzzer finds a new crash, we want our fuzzer to automatically determine whether this is a unique crash or is it a duplicate. In order to decide this, Syscaller requires a unique output for each crash. Our approach for crash deduplication could be categorized as YOLO, because you only live once. We use QEMU to read crash info red stack and search for all the addresses that lay within the traced module, in our case, LXCore sys. And we output the first few offsets in the module that we trace. It looks something like this. So a quick recap. We had a SSH server, coverage check, crash detection, and symbolizer check. So before fuzzing, we started with a sanity check. But we didn't have a WSL bug, so we used KVM to patch LXCore kernel code in order to emulate the bug. The fuzzer was able to find the injected bug within minutes. So we felt like we were ready to run the fuzzer. So we started fuzzing WSL. And then it rained bugs. Well, not really. A short time after we started the fuzzer, we noticed a crash with critical structure corruption, and we were like, what the fuzz? Quick Googling showed that it's PatchGuard. So why did PatchGuard come to our life to crash our machines? So let's return to how we detect crashes. So if you remember that in order to detect crashes, we added a patch to Anthos. So good news, everyone, PatchGuard is working. We first tried to enable kernel debugging, but that caused random hangs in our guest. What we eventually did was to write a small driver called Panic Reporter, which will register with Anthos a bugcheck callback using k-register bugcheck callback. So now, when the kernel crashes, Anthos will call Panic Reporter, which will issue a hypercall notifying on a crash. We ran the fuzzer again, and we got a new crash with different error code. Unfortunately for us, the crash did not reproduce. We spent hours reproducing the bug, but root causing a bug from offsets and random junk off the stack proved really difficult. So clearly, our first symbolize attempt didn't go well. At this point, we said, let's use a debugger to capture crash information and use that for deduplication. Unfortunately, running KD on Linux machine was not stable and very slow. It took us several minutes to get the crash down. So we opted to use a Windows machine for running the debuggers. We set up the Windows guest with a network kernel debugger enabled. We built a small Go UDP server that would listen for connections from guests and connect them to the debugger with a script to create a crash down. This entire setup is hosted on a Windows machine where KD and symbols are working. That worked well, but for like 5 minutes. But when we scaled it up, the connection with a debugger would sometimes be cut off and not recover. This would cause a guest machine to hang. In addition, in the process of reproduction, Syscaller attempts to minimize the crashing programs as much as possible, meaning it will crash the machine multiple times and wait for the crash logs to see if it's the same crash. So now, creating crash dumps was a bottleneck for the fuzzing process. So we realized we need a better solution. We took a step back and asked ourselves, how are KD and WinDebug are able to generate call stacks, sorry. The answer is they use dbg help DLL. It contains a function called stackWalk, which will iteratively walk the stack and restore the context record for the relevant frame. We could use it to produce a full call stack and symbolize it using sim from address function. To use it, we had to get a few things: the stack frame, CPU context, and implement a function that reads the guest memory. The final symbolizer architecture is really awkward, but it works as follows. On the Windows machine, we run a server process that exposes a stackWalk-like API. When the test machine crashes, QEMU reads the stack, the module addresses, and the registers using KVM and sends it to the symbolizer. The symbolizer then calls stackWalk with all the relevant arguments and retrieves a call stack which will it send back to the QEMU. This architecture was heavily inspired by Boxpawn for Windows. So after a lot of agony, we got from these random numbers to this beautiful call stack. Look at those pretty symbols. We don't like running Windows machine alongside our fuzzer, so we asked ourselves how hard it will be to implement a minimal version of a KD in Go. So we started developing KD Go, which includes a PDB parser and downloader, a stack unwinder that uses symbol unwind info, and a KD protocol client, which we implemented for KD serial. KDNet will be available in the near future. It's not perfect, but we got it to compile into Syscaller and to symbolize crashes directly without the use of another remote machine. Now Yoav will come and talk to you about our next problem that we encountered.
So the next issue we got was coverage stability, or our coverage instability. So Syscaller uses multiple threads to detect data races. But in our coverage implementation, we only had one coverage buffer for the entire process. So in practice, the same program running multiple times will result in different coverage traces. Coverage instability hurts the fuzzer's ability to find new code paths and thus finding new bugs. So we had to fix this issue, and we said, let's do it like KCOV. So in order to do that, we had to do a few things. The first is we needed to be able to track threads in the guest in order to swap PT buffers for each thread. And we also needed to add a handle-aware API to KVM so we could fetch different coverage traces from different threads using a handle. So thread tracking, we started with trying to find a way to get thread tracking from KVM. The first thing we did was to peek at get current thread, and we found it uses GS with a specific offset to get a pointer to the current E thread. On Windows x86 machines, the GS segments point to KPCR, which is the kernel process control region. Then we went to the swap context function in CentOS, which is used for context switching between threads. We started looking for a good hook. Near the end of the function, there's a call for swap.js, which swaps the current JS value with the one in IAA kernel JS base MSR. In VMX, we can trap on MSR writes, which in other words mean we have a callback on a context switch back to KVM. So our implementation for thread tracking is actually pretty simple. We started with disabling the disable for the intercept of GS base. And we added code in KVM to swap buffers on each GS change. And finally, we added to Panic Reporter code to notify KVM on thread termination because nobody likes memory leaks. So that in that way, we can release the physical memory back to the host. So if we put it all together, when syz-executor starts, it will spawn a few threads. and register them with KVM. KVM will allocate PT buffers for each thread and start recording coverage for all of them. Let's say if thread 3 tries to issue a system call, it would be recorded. But if an evil thread will start running, the coverage trace will stop until the thread will resume execution. Finally, if the thread dies, Panic Reporter will notify KVM, which will release its physical memory. So in hindsight, we're all much smarter. And when we looked recently at the swap context function, we found references to IPT-sys. Quick Googling brought us to Alex Ionesco's Gita page, which provides some more details on IPT-sys, which is apparently an Intel PT driver used by Microsoft for tracing Windows kernel, for tracing Windows. It has support for per-thread tracking, which is pretty cool and would have saved us a lot of time and pain. But it doesn't support kernel trace because it has an if statement that does not support it. So in hindsight, we could have bought an Ice Lake server, which has support for VMX Intel PT virtualization, and wrote a small patch to IPT-sys that would allow kernel trace to trace kernel instead of using a modified KVM. We had other issues, like we had autoloaded programs that would starve our fuzzers, OneDrive. Windows Update would restart our fuzzer randomly, causing Syscaller to think it's a hang. Windows Defender decided that our fuzzer is a virus. And in general, take time and make sure you adjust your fuzzer for best performance. So the results, we fuzzed for 2 weeks, and we had a working prototype for Syscaller. We found at that time 4 bugs, 4 denial of service bugs, 2 that fit in a tweet, 2 deadlocks, which are still not resolved. If you're interested, you can check out the GitHub page for WSL. We have issues there. But we found 0 security vulnerabilities. In hindsight, we discovered that Microsoft were fuzzing with Syscaller WSL at about the same time. So understandably, we did not find bugs that they already closed. But we were a bit disappointed, but we decided to move to a real privilege escalation target. And we went back to the Windows kernel attack surface map, and we decided to set our sights on Win32k. First, what is Win32k? It's the kernel side of the Windows subsystem, which is the GUI infrastructure for the operating system. It includes 2 major parts, the user, which is also known as the window manager, and GDI, which is the graphic device interface. So why Win32k? Well, first, because it's a very popular target for local privilege escalation, and we're looking for local privilege escalation. And second, it has huge attack surface with more than 1,500 syscalls. And although it has been fuzzed before, some would say to the death, we couldn't find any previous work on coverage-guided grammar fuzzing for Win32k. And we decided if it's that complex, we're going to find bugs. So we had to do additional changes. First, we had to make changes to the fuzzer, the executor, a few changes to IPC because we're moving from Linux to Windows, and minor changes to the coverage. Our first attempt at porting was to change the extension to .exe and hope for the best. But since that didn't do the trick, we had to do like real work. So the first, we had to do changes to the executor, which was to support up to 12 parameters per syscall, because you know Windows. Then we ported some OS-related changes around thread management, shared memory pipes, to name a few. We had to expose Windows syscalls to the executor. And we decided to build everything on Linux because it was much easier for us, but it caused us a few headaches. So the method for building all of this on Linux starts like this. You start with Windows DLLs. Then you use a tool named gendef to generate def files. Then you use another tool called MinGW DLL tool to generate import libs. And finally, you link it all together to your happy executor. We had to do some changes to the fuzzer. Again, small things around IPC and memory. And we had to add the entire Win32k grammar, which we'll talk about extensively in a few slides. For coverage, we had to do a few changes because Win32k is not one thing, but 3 things. It's actually Win32k base, Win32k full, and Win32k. And unfortunately, our Intel PT decoder only supported one module. We solved this issue by moving to WinAFL's Intel PT decoder, which has also support for multiple modules, and as a side effect, is much faster. And finally, we can get coverage traces for Win32K. So to recap, we modified the executor, we changed something in IPC, fuzzer, and coverage. We moved to a sanity check, where we tried to reproduce CV 2018-0744, which we've seen earlier, but it did not reproduce. Turns out our fuzzer was running under session 0 and not under normal user session 1. We fixed this issue pretty quickly by moving the SSH server from being a service to being a normal startup program, but the main takeaway from that is it's important to test your fuzzers and make sure you reproduce all bugs, otherwise you're probably just wasting CPU. Then we moved to coverage stability. We moved to fuzzer stability, where we added 15 APIs and we let the fuzzer run for the night, and we got a blue screen. Our first thought was patch guard, but the bug was reproducible without the fuzzer, so we gave it a second look. The first bug was really weird. It was a use after free in open clipboard, and it was only reproducible on a few machines. And we were like, what the fuzz? Unfortunately, looking at the crashing program did not reveal any significant clues about the root cause, so we had to do a real work. So looking at the crash site in IDA, we can see that the code is trying to fetch the process ID, but the process information is freed before use. So what we discovered is that on machine that the bug reproduced, the if statement above the block evaluates to true. What does it check? Well, it checked that an ETW Win32K trace logging provider has a specific feature turned on. What we found out through experimentation is if we were to install the same machine a few times, sometimes this flag would be on and sometimes it would be off. And it felt like our fuzzing machine was probably some part of a feature experiment. So I don't always get an A/B tested machine, but when I do, I get a vulnerability in it. So we went back to check instability. We reinstalled Windows and made sure that the flag was definitely off this time. And we got another bug. This one was actually pretty interesting. It's a denial of service in register class EX, which only required one syscall, which was odd. But the bug itself was not really in Win32K, but in RTL allocate heap. Apparently, when requesting allocations in specific sizes, RTL allocate heap will try to allocate a memory from reserved memory off the heap and crash while reading non-committed pages. So at this point, our motivation was really high, because with 15 syscalls, we found 2 bugs, and with 1,500 syscalls, we're going to find 200 bugs, right? So what we decided to do next is to create a full grammar for Win32K from scratch, which is a pain. Our first thought was, let's automate this, but we had a few obstacles. The first one is that Windows header do not convey enough semantic information to generate quality grammars from it. And the second thing is that there are undocumented Windows API, so we had to do more work. Fortunately for us, Windows is technically open source, because there's the Windows NT leaked sources, there's the Windows 2000 leaked sources, there's ReactOS, which is technically Windows 2003 leaked sources, there's WRK, and a few other resources. So what we actually did for each syscall is we looked at the sources and the documentation in SDN, and we tried to verify as much as we can in IDA. And we basically became union workers in the grammar mines. Most APIs are pretty simple, but others have complex input structures with complicated semantic relationship that was really a pain. Here's a few examples of grammar that we added. You can feel the pain while reading this. So we let the fuzzer run, and within a few hours, we found 3 new vulnerabilities in GDI. And we let the fuzzer run for another week, but it found nothing. And we felt we want more. So at this point, we had to go a bit deeper. And I'm sorry to disappoint many of you in the audience, but fuzzers are not magic. which means that we, as researchers, need to teach them tricks and help them to reach how to reach attack surfaces in order for them to find bugs for us. So our method for doing this is we try to learn as much as we can about the attack surface we're targeting, bug classes, prior work, anything that we can get our hands off. And we try to reproduce all bugs because they give us information about, they teach us a lot about the attack surface, and they teach us a lot about the limitations of our fuzzers. And finally, we take time and look for coverage, because coverage also shows you the things that you don't know are missing from your fuzzing campaign. We take all of these insights and we try to inject them back into the fuzzing process. I know this is pretty abstract, so let's give it a concrete example from our research. One weird Win32k trick is there's a thing called GDI shared handle table, which is a table of handles pointed from the PEB. It's basically an array of structs that has all the handles relevant for GDI. Handles with process ID 0 are global handles, meaning that they are that you can use them from any process, even though you haven't created them. So we thought maybe we can use them in our fuzzing process, and that would yield new bugs. So we created a new pseudo syscall that what it does is traverses the array and searches for global handles. And we let the fuzzer run, and within a few hours, it found CV 2019-1159, which is triggered by one syscall and a global handle. The results of the research is we fuzzed for 1.5 months in our spare time. We found 8 vulnerabilities. We got assigned 6 CVE. 1 is duplicate and 1 is still pending. And we found 3 denials of service bugs, 1 crash in WinLogon, which we are having a really hard time to pin down, and a few deadlocks. So we told ourselves, LP is fine, but can we make it an RCE? So enter the Windows Metafile format, which is like all good things designed in the 90s. It supports both vector graphics and bitmaps. And if I were to summarize that image format in a sentence, it would be basically if you took system calls and serialized them into an image file. Microsoft extended WMF a few times with EMF, EMF Plus, and EMF Spool. And if you're interested to hear more about this, about WMF in general, you should check out Jure's research on the topic. So we looked at the spec for EMF, and under the bitmap record types, there's a record type called stretch BLT. And we happen to add a vulnerability in stretch BLT. So we can do a demo. You can see that's almost fully patched Windows because we recorded that last week. We're using in front view because Word was a bit annoying, but we get a crash. So for future work, we want to fuzz DirectX, which is currently we didn't fuzz because of limitations we encountered in Syscaller, and also Win32k callbacks, which are a big attack surface for Win32k, generally user mode callbacks. Also, we have a pretty big corpus of programs, about 450 programs. And we want to try them out with new bug oracles that will be able to detect crashes in a more precise manner. We want to open source our port, and finally, we want to fuzz the rest of the kernel. So to recap, we started from our user space bugs, but we wanted a kernel one. We looked at KFL, but it wasn't good enough, so we moved to Syscaller. We started porting to WSL. We were a bit disappointed that nothing happened. We moved back to Win32k. We did a lot of grammar mining. We got 8 bugs. We were able to turn some of them to RCs. And we want to say special thanks to the Dynamics tool teams at Google for creating Syscaller and a lot of other infrastructure around it. It's amazing. To Omri Ershkovitzi, who helped us making these slides really pretty. And also one mentor for his special assistance in the project. Thank you. Yeah. So yes, a lot of like the Windows headers, like when it says a D word, does it mean a D word or a flag, or it could be an atom, which is a pointer to something, or it can be like a lot of things which are not a D word. So it doesn't have enough information to effectively fuzz it. If the execution speed for kernel fuzzing was at the same speed of user space fuzzing, would probably be able to get away with much less accurate grammar than we had to do for Win32K. Yeah, there.
Thanks. Thanks for sharing. Thanks for sharing. Thanks for sharing also the approach that didn't work. How much time take to do all this research and continue to work after you spend, I think, a lot of time to see something that is not working? And
so we described the things that didn't work because they were important to us to describe them. But the entire research was about in a span of 4 months, where we did it in our 20% time at work. Okay. So it wasn't a huge effort. We had some advantage because we worked on similar things in the past, and we could start more easily. And we were also standing on shoulders of giants that made a lot of things in the space, so we could reuse a lot of things.
Okay. Thanks for your talk. You showed that Windows had blue screen of death because of use after free.
Mm-hmm.
Do you know how does it detect use after free cases?
I said it earlier. We added special pools for Win32K base, Win32K full, and others, so we can catch a pool for double freeze and this kind of stuff.
It's built-in features in Windows, and you can designate which drivers you want their pools to be tracked. It has a performance penalty. It uses something very simple to electric fence, like when you have guard pages in each side, and so that's how it does it. And it also delays returning memory back, so we can detect use after freeze.
Thank you.
Anyone else? So everyone else is apparently still processing the info.